All right, so while we're opening to page 10, here's a look at our calendar. Today is class number 28. All right, here's some quick arithmetic for you. 28 divided by 42, what does that reduce to? 28 divided by 42. What does it reduce to? Isn't it 2 over 3? Both of those, you guys don't know your 14 times tables? Both of those are divisible by 14. So today is the 2/3 mark in terms of Monday, Wednesday, Friday classes. I know that we're tired and I know that we're battling like the cold and all that stuff. And I'm just trying to say that we are getting there. It's 2/3 of the way through today. Another nice thing in terms of our calendar, this is the first time you can see what projected on the board? Final exam. So it's finally on one screen. The final exam is May 18 for what it's worth. But about 6 weeks from today, we will be completely done. So keep pushing. All right, so on page 10, we'll start here with number 1 in the middle. Can we go to Vance? Okay, so let's look at the first equation. You can see here there's a couple of angles. One of the angles is 2x. The other angle is x, yes? This is the first time we are trying to solve an equation where there's two different angles in there. And so the first hint that Vance read to us is that it's usually better if you can get it to be the same angle. So here we're going to start making use of some of our double angle identities. So sine of 2x, it's an identity that we saw last class. And it's actually one that I think you're going to want to try to use on the quiz. But sine of 2x, anybody know it from the first page of the packet? That right there is an identity. It's on the first page. Sine of 2x is the same as 2 sine x cosine x. The other part I'm just going to copy. I'm quite happy with it already. It has x as the angle. Okay, it's very tempting to divide everything by sine of x. We saw in the questions of the day last time that is a bad idea. What is better than dividing by sine of x, which makes it disappear? Is factoring out sine of x, right? Don't divide by it. It disappears if you do that. The better is to factor it out. Sine of x. In fact, we can also factor out a number. What can we take out of both? Take out a 2. Okay, what's still in the first set? We have a 3. We also have when you factor out 2 sine of x from that term, just 1. Okay, and now we have turned that subtraction problem into a multiplication problem. There's the times, which means we can split it up into 2 easier equations. Either 2 sine x is 0 or 3 cosine x minus 1 is 0. Okay, first equation says we want sine of x to equal 0. There are a couple of nice points on the unit circle where that's true. Can you guys point? Left-right points or the up-down points? Where is sine equal to 0 on the unit circle? It's either 0 at the left and right or 0 at the top and bottom. Sine is the y, that's the left and right. So the left and right angles. All right, so what's the left angle? 0. What's the right angle? Pi. And then in theory, there's one more answer, 2 pi. It's kind of artificial to allow 2 pi in there because 0 is the same, but anyway, that's what it says. So that's the solutions to this part. 3 cosine x minus 1 is 0 requires more work, so let's do it. I guess we want to get cosine by itself, so add 1. And then after we've added 1, what do we do? Divide by 3. So we get cosine is 1/3. Is 1/3 on our unit circle? Nope. So what button are we using on the calculator? Inverse cosine. It doesn't say to the nearest anything, so what do we have, Todd? Can we go radians? Sounds good. And remember, every trig equation like this has how many solutions between 0 and 2 pi? Always expecting 2 solutions. Calculator will only find you 1. We got to find the other one. We had a few different ways to do this, but I'll just pick one here. I will draw the cosine function. And then I'm going to draw a horizontal line at 1/3. And say that the first answer we found, which is right at that dot, is at 1.23. I need the other answer. Everybody see the 2 pi minus? So then the other answer is 2 pi minus 1.23. Somebody have a number for me? Thank you. Questions on that? Okay, so let's try part B. Here we're looking to solve cosine t equals sine squared t. So I feel like we could play the same game as we did before. You know, you could bring the sine squared over. Like equals 0 is almost always the right thing to do when solving equations. The technique up above was factor out. Can you factor something out of these? No. So there isn't a whole heck of a lot to do here in terms of stuff that we did above. So the other technique that Vance read about was to get things in terms of one trig function. This one has cosine and sine, and there isn't much we can do at the moment, but you guys do have an identity that has a sine squared in it. Sine squared plus cosine squared is 1. So then we're going to use the other version of that, which says that sine squared of t is really 1 minus cosine squared. We've used that a few times. So this becomes cosine t minus 1 minus cosine squared. Is that right? Yeah, we're going to get it wrong if we don't put the parentheses there. So I try to fool you guys, but it just doesn't work. Catch me every time. The good news is with intentionally making mistakes once in a while is that when I make mistakes by accident, I can pass it off as being, oh, I did that on purpose. Okay, so let's see if we can write that slightly differently. I've got a cosine squared, which I'll put first. I've got a cosine, I'll put that second, and then a minus 1. What kind of an equation is that? Yeah, it's a quadratic. Like normally it's x squared plus x minus 1. So call it that if you want to, but if you're comfortable leaving it like this, then great. If we're lucky, it factors. We're not lucky on this one. So what do we do with a quadratic when it doesn't factor? Quadratic formula. Can you guys try the quadratic formula? Check in with your neighbors. Okay, so we do quadratic formula. Did everybody else get this? -1 plus or minus root 5 divided by 2. Okay, so we've got two different numbers there, and recognize that that's what cosine of t is equal to. Like when you solve a quadratic equation, normally it's x equals blah, but in this case it's cosine t equals blah. And so we are going to have to take the inverse cosine, or the arc cosine. First, let's get that thing as a decimal. So I'll type this guy in over here, -1 minus the square root of 5, and then divide that by 2. And what do we think about taking the arc cosine of that number? It's not going to work. Cosine always gets up to 1 and down to -1, and if it's outside of that interval, it's not going to work. Though if you really want it to yell at you, I guess you can ask it for it, but it's okay. Apologies. So that wasn't it. So how about we try the plus version? So -1 plus root 5. We take that, we divide it by 2. Okay. No, indeed. I don't know where 6 came from. Divide by 2. Okay, 0.618. That's going to have a legitimate angle coming from it. So we do the inverse cosine of that number. Make sure I'm in the right mode. We're in radians. Inverse cosine of the 0.618, and I get about 0.9. And just like up above, expect two answers. I kind of feel like it's going to be the same technique to find the other answer. What do we do? It's going to be a 2 pi minus. I think for cosine, it's always a 2 pi minus. So one answer is this. The other answer is 2 pi minus that number. So we've got two answers here. Questions on that? Yeah, Chris. Mm-hmm. So first in my mind, distributed, that's a -1 and that's a plus cosine squared. And then I just decided to change the order because I kind of knew it was going to be one of these quadratic things. And so that's why we did it. Yeah. Other questions on that one? Okay, so last class Garrett had asked, so we've got these identities, so what are they for? And I had given him some reason you could make a bigger table with trig functions in it. Well, here's another reason we care about identities, is that if you need to solve this equation right here, I just don't think we can do it without using an identity. Same thing down below. So having these identities kind of builds up our toolkit. Like you can't solve quadratic equations until you know how to use the quadratic formula. You can't solve trig equations until you are equipped with the right identities. So it just gives us more things that we can solve. Okay, number 2. 2 will go to Kyle. Okay, so a whole slew of symbols right here. I don't need you to digest them all at this moment, but for example, cosine of a minus b is the same as cosine a times cosine b plus sine a times sine b. And we call that a difference identity because it involves the cosine of the difference of two angles. And then there's 3 others that look just like those with pluses and minuses, sines and cosines. All right. Okay, on the next page it says we're going to prove this formula. All right, let's give this a shot. Put your pencils down because I'm going quicker than I want you to be able to copy. So I want to prove to you that cosine of a minus b is given by that formula that we just read. So here's a proof. Take a look at this picture right here. We've got two angles. You have angle B is the small one, and then angle A is the big one. Notice they both start from the positive x-axis, and that's a unit circle because of the 1. You guys buy the coordinates there? Cosine and then sine, cosine and then sine. It's a unit circle, so it's okay. All right, so here's what we're going to do. We are going to find the distance between the 2 points on the circle above left. We're going to find the straight line distance of that. And we have a distance formula, right? Big old square root, x1 minus x2, all that. So we're going to subtract those guys. Cosine A minus cosine B. That subtract the x's square plus. Then we subtract the y's. What am I doing wrong here? Subtract the y's and square. And that right there is the distance between those 2 points. Then we're going to do a bunch of stuff in our head. Quick. If you FOIL the first thing, you get cosine squared A, right? That's the first term. If you FOIL the second thing, what's the first term? Sine squared A. When you add cosine squared plus sine squared, you get 1. The middle terms, when you FOIL, you've got a minus cosine A cosine B twice. Minus 2 cosine A cosine B. I already kind of start to like this because that is part of the formula that we're after. You can take a look at it if you want. Then we're going to FOIL the second thing. We get minus 2 sine A sine B. I like that as well because that's in our thing. Sine A sine B. And then if I square the last terms, what do you get in the beginning? Cosine squared of a, is that the wrong letter? No, that's okay. Yeah. Cosine squared of B. If you FOIL the second one, you get a sine squared of B. Cosine squared B plus sine squared B is plus another 1. So that right there is really a 2. Okay, we're going to pause right there on that one. And we're going to take a look at the other picture. Imagine taking this whole picture, this whole angle right here, and keep it fixed to the origin, but rotate it by b degrees clockwise. What happens to this line right here? It goes onto the 0 line, right? So you just rotate it by exactly the right amount. That's what I'm trying to do. Just rotate it so it goes right onto the 0 line. Then if we rotate it, then what's the angle that's left over in between? Isn't it a minus b? That's that angle in there? Okay. So then that triangle is now sitting here with an a minus b, but it's now on the x-axis. And if the angle is a minus b, then do you like this part? The cosine of the angle, comma, sine of the angle. Okay. Next thing we're going to do is find that distance. Same distance formula. The square root of all that stuff squared. So let's try it. See if we can keep that on the screen. Square root of, we subtract the x's. That's cosine a minus b. And this is the 0.10. So we subtract those x's and square. Plus, then we subtract the y's. Sine a minus b, what's the other y? Minus 0 squared. Everybody see it? X1 minus x2 squared plus y1 minus y2 squared. Okay, I'm going to scroll that picture off so we have a little more room. We're going to FOIL here. First term we get is cosine squared of a minus b. How about when we square this guy? Sine squared of a minus b. What is that equal to? You add them. 1. If you FOIL and do the last terms in here, what do you get? 1. So altogether, 2. And then we're doing outers and inners. When we FOIL the first thing, we're just going to get minus 2 cosine a minus b. Lots of FOILing, lots of distance formula. Nothing hard, just we're kind of omitting some of the details. All right, now we put these two ideas together. What must be true about that green hypotenuse and this green hypotenuse? Must be the same. All we did was rotate the triangle. We didn't change any lengths, we just rotated it a little bit. So all these massive calculations that I ended up doing must be equal to each other. So let's set them equal to each other, but do a lot of algebra in our heads. So we're setting this entire thing equal to that entire thing. Let's get this out of the way. Imagine they are equal to each other. How could you get rid of the radicals? Square both sides. So imagine they're not there anymore. I have a 2 in the front of both. What can I do to both sides? Subtract 2. Now the 2's aren't there. I'll write down what is there. -2, this is the top one. Cosine A, cosine B, minus 2 sine A, sine B. And that is now equal to -2 cosine of A minus B. Now what can I do to both sides? Divide by -2, so all those -2's go away. And if we divide everything by -2, you'll end up with exactly that. Okay? Okay. All right, the other three, once you know one, it turns out the other three are easier to figure out. So Chris, can you read 4? Okay, let's go to Richard for 5. Okay, so let me write down one of the formulas from the previous page. You don't need to copy this, but here's something that hopefully we believe, or at least we believe it's reasonable. This is one of the identities from the previous page. This is how you deal with sine of the sum of two things. This thing down here is an identity that I gave to you last class, but I said we'll prove it next time. So here's the proof. Turns out to be really easy when you have the right tools. I'm trying to figure out what sine of 2 theta is. What should I replace A and B with in that top left? Theta plus theta. Do you see it? You can get a sine of 2 theta by just calling both of these guys thetas. Got it? That's now sine of 2 theta. So all we have to do is replace everybody here with theta. So let's see. Sine theta cosine theta plus sine of theta cosine of theta. Right. So that's really 2 sine theta cosine theta. And there you go. Just prove the double angle formula for sine. Let's try this cosine one. This is one that's on the previous page. So we're kind of believing that one. How do I build a cosine of 2 theta from that formula? Make it theta plus theta again. So cosine of theta plus theta equals cosine theta times cosine of theta minus sine theta sine theta. And then that first term is really cosine squared theta minus sine squared theta. So that's that identity. Okay, let's move on to the next page. Part B. I think we're up to Kate. Okay, so was this one of the questions of the day or no? We did 15. Okay, so same idea. We're trying to get sine of 75 degrees, which means what you want to do is take 75 degrees and build it as a sum or difference of angles that are on the unit circle. So how can you build 75? So we could do 90 minus 15, but the reason I'm not going to do that is because I don't know personally the sine of 15 degrees. You might know it because of your questions of the day, but 15 is not one of our nice ones on the unit circle. Test today? Everyone agree? 30 and 45 are both on our unit circle. So now it's a matter of using the formula. I'll put it up here again and then ask you guys to do some work. So this is sine of A plus B. Okay, so the formula says to do what? Sine of. Everybody okay plugging into the formula? Okay, and then if that unit circle is still handy, then these should all be easy to pick off of the circle. And so if we just merge these together, I've got a radical 2 plus, how much is root 2 times root 3? Root 6, we know we're allowed to do that. What's the denominator? 4. Root 2 plus root 6 divided by 4. That's it. That is what sine of 75 is. And so if you wanted to, you could confirm your answer numerically on the calculator. So I can type in root 2 plus root 6. And then divide by 4. I get that. And in theory, that's what the sine of 75 degrees is. Sine 75. Hey. Wrong mode. Let's try again. Sine of 75 is that. So I don't know. I think it's kind of cool. You can take any sum or difference of any of these things that are on the unit circle and build new things that you could put on the unit circle. And once you have new things like 75, what could you do? Couldn't we build new things based on the new things? So like, you know, if you have patience, you can find the exact values of a lot of things because you now have the ability to do sums and differences. You also have the ability to do doubles and halves. I don't think we do half angle stuff, but I guess we don't need to talk about it. This is one that I did. When Garrett had asked the question the other day, we ended up doing something like that. So this is fine. Let's see if we can go down to C, acetate. Okay, so cosine theta plus pi over 6. We're going to look for a cosine formula that has a plus in the middle. So again, you've got all these are on the first page too, aren't they? Yeah, all four of these identities that we're playing around with now are right here on the first page. Right down here. They have kind of funny letters in them. What's the first one? That's a theta. What's the second one? It's phi. Yeah. So you've got all of them up there. Just have to be comfortable with thetas and phis. So let's see if we can build this formula. Okay, so I'm just copying the formula that's on the page. And then we're going to plug stuff in. So instead of A, what are we putting? We're putting theta. Instead of B, putting pi over 6. Okay, and then it's just a matter of grabbing stuff that's on the unit circle. Cosine of pi over 6 is sine of pi over 6. Okay, so there's another way to think about cosine of theta plus pi over 6. Now, if I'm being honest, that way seems more complicated than just the original cosine of theta plus pi over 6. So really, I didn't give you this example to show you a nicer formula. Let's take a look at 6. Emily. Okay, does everybody understand the goal here? You're not going to have gone through this whole work. I'm just going to give you this thing here and ask you if you can bring it back. Was it really cosine of theta plus something? And in this case, maybe we get lucky and we recognize, oh, it's just pi over 6s that were in there somewhere. Let's go to Todd. So taking a look at that, so I'm looking here, I see a 2 in the front. Is that going to equal like the cosine of some angle or the sine of some angle? No, sine and cosine never get above 1. Okay, so then like clearly we can't just look at it and hope that we get lucky and say, oh, it just came from pi over 6. Let's keep going here. Is it even reasonable to think that 2 sine of t plus cosine of t looks like a single trig graph, a single sinusoidal function? I've got sines and I've got cosines, and they're adding together. So sometimes they're going to both be positive, and they'll build up higher than either of them would have gotten. But sometimes one is positive and the other is negative. When we add them, they'll kind of have some cancellation. Let's take a look at the graph. I mean, like it could be, it's difficult to visualize what the graph of that thing might look like. It seems complicated. So let's go into y equals here, and we'll type in that new thing, 2 sine of x plus cosine of x. And let's see, negative 10 to 10 is probably okay. But this guy isn't going to get much higher than, I don't think it could get above 3. So let's just go minus 3 to 3. And you know what, maybe we'll just do negative 2 pi to 2 pi. Any guesses? I would like to be in radians. What am I in? Thank you. 2 sine of x plus cosine x. Is it going to have like crazy ups and downs? Sometimes the highs are not as low as the lows. And, you know, is it going to be something like this where like sometimes, you know, like it could look like that and then down and then, you know, like they're working together and they're working together in some unknown way. It could be quite complicated. Or it could look like that. If I just showed you that graph, what would you think you were looking at? Just a single sine wave, right? Sine of something, cosine of something, right? Doesn't look at all like this complicated thing that I was predicting. Topher. That's what it looks like. It looks like it's been shifted, right? It doesn't start in a nice place on the y-axis. So there's a shift thing happening here. How high does it get? Is it 2? Looks like it's over 2. So yeah, there's some stretching thing happening. Like I see a 2 in the front and I see a 1 in the front. Somehow that ends up getting a little higher than 2. What about the period? This is minus 2 pi to 2 pi. What does it look like? That looks like 2 copies there. So what does it look like the period is? Looks like it's 2 pi. Okay. So can we somehow come up with a way to write that as a single sine or cosine function? That's the goal. And I'll tell you why that's the goal. If you have could you guys picture, like hanging from the bottom of this table right here, a spring. You guys are going to take physics next semester, a lot of you. You're going to be playing with this spring, and attached to the spring will be a mass. And if you pull the mass down and stretch the spring more than it wants to be stretched, and you let go, what will happen? Then it'll go up, and then it'll go down, and it'll go up and go down. And if we ignore friction, then in theory, it'll just go up and down forever, the same height every single time. And it turns out, to figure out where this thing is at any moment in time, you end up needing to solve something called the differential equation. It involves calculus. And the solutions to those kinds of differential equations look like that. Something in front of sine plus something in front of cosine. And it doesn't just have to be a spring. It could be anything that does that kind of oscillating thing. For example, electricity. Maybe some of you guys know about it. It's, you know, highs and lows and peaks and valleys. And you can solve a differential equation and figure out exactly what the current is at any moment in time. And you will get some answer that looks like that. But that is way more complicated than it appears. That looks like a single sine or cosine function. So that's why we're after this today, is because this thing in yellow is a natural answer, but maybe we'd prefer it in a different form. So let's try number 7. We're up to Stephen. Okay, are we ready to embrace? You might want to stretch. First, let's make sure we're clear that like this is the same kind of question we were asking before. You have some number in front of the sine, some other number in front of the cosine. That's what we had. And the goal is to maybe write it as some amplitude, which we don't know yet, times a single sine function. What is this phi business? It is a variable, but what was it called in terms of the graph? That was a phase shift, right? That's the shifting it off a little bit. The b that is here is a copy of the b that's over there. So that part seems easy enough. The period looked like it was 2 pi. You just copy the b over. Okay, so here's what we're going to do. Let's start with this thing. A sine of b t plus b. We had a formula that we saw today that seems appropriate to use here. What was the formula? Yeah, didn't we have a sine of, what do you want? A plus b, that's the formula that we had. There's a plus sign in the middle. That's a sine function. Seems like this is what I want. I'll put it here so we have it for reference. So this equals a in the front of a whole big mess. Instead of this a, what are we putting? We're putting bt. Instead of b, what are we putting? So can you guys fill in the big parentheses here? Any questions on the substitution? Okay, so it looks worse, so that's all right. Next thing. I got the whole idea is to try to build this. That's what I want this final thing to look like. Okay, well, let's see. I feel like I'm kind of getting there. I see a sine of BT, and I see a sine of BT, and I got a cosine of BT, and I see that over there. How about we distribute this capital A first? In fact, just to save a little bit of writing, I'm just going to get rid of the brackets. Oh, oh. We're going to get rid of the brackets and just distribute that A through. So there's an A in front of this, and also an A in front of that. Is that okay? Okay. So if we're going to try to find something that's supposed to be that sine of BT term, then it feels like that needs to be this. That's the one that has the sine of BT in it. And the other one has a cosine of BT, and this guy has a cosine of BT. Buy it? With a plus sign in the middle. Maybe we'll just erase so you can really see that plus sign. So that plus sign is separating our two terms. Okay, so if I'm going to make those two yellow things equal, then I feel like I got to make some other stuff equal. I've got the sine of BT is here, and the sine of BT is here. What's left in the first thing is this A1. What's left in the other thing? A cosine of phi. If I'm going to make the yellow things equal, I have to pick A1 to equal A cosine of phi. A1 equals A cosine of phi. Do we see it? And if we see that, then can you write down the other equation to make the greens equal? Why is that? Mm-hmm. Mm-hmm. That's right. It's substituting. That's a good word. Okay, let's prepare to do some math. The goal here is to figure out, I got to remember what we know. We know 2 sine of t plus cosine t. That's what we're given, which means we know the A1 is 2. And we know the A2. How much is it? It's 1. So we know those guys. We know A1 and A2. We are trying to find the A and the phi. You have 2 equations. You're trying to solve for capital A and phi. Okay, first thing I'm going to do is divide these equations by each other. What really nice thing happens when you divide? The capital A's cancel. I actually would like to divide in the upside down order from what's given here. So let's flip everything in our minds. A2 divided by A1 equals sine phi divided by cosine phi. Right, just flipping it over. So A2 over A1 is really the tangent of phi. So in this example up in yellow, we know the A1 and the A2. Those are just numbers. Divide them, take the inverse tan, you just found your phase shift. You just found phi. They're given to us. We're starting with this. And A1 and A2 are just these coefficients. Yeah. Okay, to find capital A, that's the other unknown we're after, I'm going to do something kind of funny. I'm going to take both sides, both of these equations. I'm going to square them, and I'm going to add the 2 equations. So on the left-hand side, you square it, you get A1 squared plus, we're going to add the other left-hand side, square this one, a2 squared equals. Square the right-hand side, a squared cosine squared of phi plus, what's the other one? So that was 2 steps in 1. Are we embracing the struggle? Well, it's not clear why we're doing this, but if I want to square one side, I have to square the other. So I guess what I'm saying is you square both sides of both equations and then add them up to create one new equation. It's a strange thing to do.
Always just divide one equation by another whenever you want without changing anything.
Yeah.
It's always fine.
Yeah. It's something that you do all the time. You did it. Where did we do it? We did it right here. How do we solve this equation for cosine x? What's the first step? Add the 1 to both sides, and then divide both sides by 3. So you're using the fact that 3 equals 3, and you're dividing both sides of 2 equations. Yeah, because we never write the 3 equals 3 and then say divide both equations. So we have substituted the value for a. Oh, yes, we don't know capital A yet. Yes. Do you know phi?
No. But probably we could solve phi.
Yeah, so we did solve for phi over here, and then yes, once you know that, you could bring it back here. But I'm going to give you a simpler equation to just get capital A. So here it is. If you factor out a squared, what's left? And what is cosine squared plus sine squared? It's 1. That's why I did that very strange thing where I squared both sides and then added them. So what that means is that our 2 equations are down below. Capital A squared is a1 squared plus a2 squared. And the tangent of phi is a2 over a1. Okay, I have like 50 seconds to show you what all that is used for. So let's do it. These are 2 equations. We're going to see them in a different context soon, but we just proved those 2 equations are true. But on the next page, it says you have 2 sine of t plus cosine t. That's what we started with. This is really a1 is that number, and a2 is this coefficient. It's 1. So now the goal is to find a. And here's the equation that we know is true. So we're doing a1 squared, which is 2 squared. A2 squared is 1 squared. How much is that? That is 5. So how much is a? Square root of 5. Square root of 5. Let's come back to my calculator here, and then we'll wind down. Remember I asked you how tall this thing got? You guys said 2 point something. How tall is it exactly? It is the square root of 5. That's how tall it is. And the last piece of this puzzle, which and I'll end here, is that we need to know the phase shift, right? Looks like this guy has been shifted a little bit. Like normally sine would start at the origin and go up, but instead it's off by a little bit. If you want to find exactly what that phase shift is, you know that the tangent of the phase shift is a2 over a1. 1/2. What do you type in? Inverse tan of a half. That tells you how far you have shifted. All right, so I know we're out of time, but if you don't mind bearing with me for just a moment, I am now typing in my final thing. Square root of 5 times the sine of x plus, and then inverse tan of a half. I don't know what it is, but I'll just type it there. If I have done this correctly, what should I see? The same thing. I'm hoping I've done this correctly. Oh, thank God. So we figured out what that complicated 2 sine of t plus cosine t is really. It is really a single sine function with a funny amplitude and a little bit of phase shift, and that's it. 6 times? What do you mean? Oh, right, right. Well, the good news is you just have to use the 2 equations that we used here. Yeah. Okay, sorry for running over. We'll see you guys Wednesday. Oh, don't forget, project is due Wednesday, and I will hand out the last math project of the semester Wednesday.